Okay, so the integral we've been using so far has been dealing with just area. Okay, the area under a curve, the area between curves, bounded area. Today we're going to start, bless you, we're going to start volumes. Okay, so, but today's volume we're going to do basically what we call cross-sectional volume, or volume by slicing. Okay, so volumes of solids with known cross-sections. So for cross-sectional area, depending on whether we're taking our volume where the cross-section is perpendicular to the x or the y, we have two different equations. Just like we had with bounded area, if we chose horizontal strips versus vertical strips. Okay? So the volume equations deal with, well, which way is my height, or which way are my cross-sections perpendicular. So the way that cross-sectional volumes work is that in the x and y plane, we have what we call our base area. And then we use three-dimensional shapes that are built by taking some kind of geometric shape and doing it in the third dimension. So in these two cases, you can see we're using basically squares or rectangles to create a three-dimensional volume. Okay, where the base shape comes from my functions, which is the area times the height based on my cross-sections. Okay? Now, it's not very different than what we were doing before. Okay? So, these are the equations that we've been working with. When we've been dealing with bounded area or area between two curves, we're talking about a two-dimensional area, length times width, where the length is determined by my function, and my width is determined by my change in x, which is basically between my limits. So my limits a to b is basically the width, and the height comes from the function itself. And as the function changes, of course, my height changes, which makes my area also change. Okay? Now the volume we're dealing with is basically this equation that you learned in like 5th grade. When you learned prisms, their volume came from big B times H, and big B was the area of the base. So the base shape is what gave the prism its volume. So you take the area of whatever base it was. If it was a triangular prism, the base area was a triangle, and then you multiplied it by the height. If it was a rectangular prism, the base shape was a rectangle, and you multiply that times the height. That's basically what we're doing here. This area is our big B times the height of our prism, which is now my limits. Just like in my original, the limits was my width, now we're talking about this being my area of my base times the height given by my integral, depending on how tall it is. Okay? So really nothing's changed other than the fact that instead of just using a function or two functions, we're going to have to create some kind of area shape based on my functions. Okay? And that's where our first example leads us. Okay? So we're going to find this volume of the pyramid. Okay? Now I know you know the equation for the volume of a pyramid. Okay? But that's not the way I want to look at it right now. So let's imagine for a second if we consider a horizontal slice through the pyramid. Okay? So if we take this slice right here, this piece, if I take that piece out and look at it, okay, that green piece, when I pull it out of this pyramid, is actually going to look like a square. Because the base of my pyramid is a square. And if I cut anywhere in between here that is parallel to my base, I'm going to get the same shape. Okay? So what's happening here is I can say the volume of this slice is s squared because the area is a square, times the change in the height, this dH. So the volume of one piece, one slice, is this. This is the volume of this one piece. This is what the area looks like, and this is the height of it from here to here. But that's just the area of one little piece. Or sorry, the volume. I don't want the volume of one little piece. I want the volume of the whole figure. Okay? But I can use that kind of idea, okay, to actually create an equation for the whole volume instead of just one slice. So this is the volume of one slice based on the fact that our height, if you notice our height and our width are the same. And that's my integral. And notice, again, this is following that formula, big B times H. Big B being the area of the base, and the height being the height of the prism itself. Okay? You'll find that a lot of the formulas that we use at the lower levels tend to come and look like a lot of the formulas that we use in calculus. So again, now it just becomes a integral problem, and look, that area of or volume of a prism or a pyramid is 1/3 big BH. And look, when you take this and you do your antiderivative, adding 1 to the power makes it cubed, divided by 3 or multiplied by 1/3. And that's where that equation comes from. And we get 9. Okay? Now, this is a very, very simple example. Okay? The hardest part about these is trying to figure out what the shape is going to look like. Okay? Now, and if you use the other equation, of course, you get the same thing. Now, method of slicing. This is what you need to do first. Step 1. Sketch a solid in a typical cross section. Okay? So you want to know what kind of it looks like, and you want to know where your cross section is coming from. 2. Find the formula for volume. Okay, note that I used V of x instead of A of x, because remember, our integral is going to be giving us volume, not area this time. Okay? Then you're going to want to find the limits of your integration. What's the height of your solid? Integrate and find the volume. It is really just that simple. Okay? Those are the 4 steps that we're going to be using. Now, Cavalier's theorem says that 2 solids of equal altitudes and identical parallel cross sections have the same volume. Okay? And all that means is that if I have this cylinder and this cylinder, they have exactly the same volume. And it doesn't look like it, does it? But think of it this way, and I know this is kind of an outdated concept, but have you ever seen like a stack of CDs? Just a stack of CDs just sitting on top of each other? It'll have a volume, right? It basically makes up a cylinder. If you take that stack of CDs and you just push it a little bit in the middle, like this, if you just take your fingers and just push it like that, does the volume that takes up change at all? No. It'll still have the same volume. Basically, it will look something like this, but it will still have the same volume. It'll still take up the same amount of space, and that's what Cavalier's theorem says. Okay? So just because you bend it in a way doesn't mean that the volume changes. Very similar to when we deal with like exhaust. If you take a 3-inch pipe and you bend it around your axle or whatever, that pipe is still 3 inches. It doesn't change. Unless you crimp it, then there's something different. But as long as the cross sections stay the same, just because you bent it in a different angle doesn't mean it's going to have any less volume flowing through there. Okay? And that's basically what we're saying, is if these cross sections are identical all the way through, then the volume it takes up is exactly the same, which is going to be an important concept. All right, so one more example. It says find the volume of the solid shown. The base of the solid is the region bounded by the lines 1 minus x over 2 and negative 1 plus x over 2 and the line x equals 0. Okay, and we're using equilateral triangles. I've already done the sketch for you. So this line here and this line here are those two lines that they gave us, and then this is x equals 0. Okay? And you can see this is my three-dimensional figure right here. This is the triangle. This base right here hits both of my functions, f of x and g of x. Okay? And then you can see it even better here. This distance from here to here. This almost looks like what we were doing with bounded area, doesn't it? Basically, this distance from here to here is top minus bottom. Okay? And that's also how we find the base of our triangle to find the area equation for that equilateral triangle. All right, so here we go. So the base and the area of each triangular cross-section are set up as this. So the base of my equilateral triangle is just like we said. It is the function on top minus the function on bottom, just like what we were doing with cross-sectional areas. Okay? That's the length of my base. So the length of my base is 2 minus x. Okay? So that means that the area of my equilateral triangle, this is the equation of an equilateral triangle's area. It's root 3 over 4 times the base squared. So this length of this base right here will create the area for one of my equilateral triangles. Then that's the area that we're going to be plugging into our volume equation. So that volume equation that we had, this one, we're plugging in that area for the equilateral triangle. Because that area of that equilateral triangle is actually going to create my volume. Just like what we were just talking about with that cylinder. That circular cross-section or that square cross-section from the pyramid actually create those volumes. It's kind of like a 3D printer. We're taking that shape and we're 3D printing it multiple times on top of each other, layering it in. So this right here becomes my equation, and it's 0 to 2 because that is where my solid starts and finishes. It starts at x equals 0 and it ends where they intersect at 2. And since they're perpendicular to the x-axis, we're using the x values, not the y values, for our limits. And then at this point, it just becomes a really simple integration problem. So you take the antiderivative, plug in your values, and this is the volume. Okay? So again, it's very similar to cross-sectional volume. That's why we did cross-sectional volume first, and we moved straight to this. Because to find this base, this shape right here, the base, we need to actually use that idea of the function on top minus the function on the bottom being the base of our figure.